Hello, this is Matt, and I'm going to be making a new GIF for my blog here, kind of inspired by this one, which I posted 2 years ago, which was kind of about how you can see how Coriolis and centrifugal forces aren't really forces, but rather they come about because of the rotating reference frame. So here, you're imagining you wanted to pass a ball to someone sitting opposite you on a merry-go-round, and the thing is you have to pass it to where they're going to go rather than where they are when you throw the ball. The red line is where it goes, and the blue line is where it seems to be going in the reference frame of the two people sitting on the merry-go-round. So from their perspective, if they don't really realize they're rotating, then it goes on a curve, so there must have been some force, they think, but really it's a straight line. Anyway, I gave code, and I give code in all my posts. If you copy that and put it into Mathematica, let's see what you get. Okay. Yep, you just get the animation, but you can kind of toy with it if you wanted to. So I guess this is here. This is the part that draws the curve. So if we make t go up to pi by 4, then we get the same. We'll see that's the blue curve that is drawn, and the trick is that we're doing a parametric plot, so this is a coordinate, and then this here is the this is then rotating it by the parameter of the parametric plot minus the time that we're at. So if this will be how much it's rotated since we got to this current point. It's a bit confusing, but I want to do something similar. So the first thing to do is to start drawing the scene, I guess. So we want to draw a circle. That's how a lot of my ideas start. Circle in the center is radius 1. And maybe draw some spokes on it. So spokes are lines from one point on the circle, sine t cos t, to another, to the opposite point on the circle, I guess. So t plus pi. So that's a spoke, but I actually don't want to use t, I guess. Let's just use, because t is more like time. We can use theta, so if you type escape, th, escape, you get theta. Theta is more of like an angle. And then I put it in a table because I want theta to go from 0 to pi. You don't need to do 2 pi because they're opposite each other. And if we do pi by 3, let's see how that looks. Yeah. Wait, is that just exactly what I did? No, I did more than that. Pi by 8 or something, eh? Pi by 4. That's what I did before. No. Anyway, it doesn't matter. Let's try pi by 3. And then let's make it all rotate. So turn it to manipulate to make it rotate. Now we use t, it's time. We can make it rotate one whole rotation. Won't do anything yet, but the spokes should rotate. So now we add t into here. Okay. And I see this lovely rotating circle. Now I want to send a point from one side to the other, so it's going in a straight line, but then see what trace it makes on the disk underneath. So just start by doing that. Let's say okay, I'll say that I'll do the point 1 equal to, so I want something that's on the circle, so I could say if I did 30 degrees here, then x would have to be minus half, and y would be square root of 3 over 2, right? So if I did that, if I draw that point on, let's start a new section, point P1. Yeah, make it a bit bigger by turning it actually into a disk, not a dig. At there. Okay, cool. And then the point I wanted to make it go to is just on the other side, like that, see? So just to check that that looks correct. Yeah, so from here to here, and then see what path it makes on the rotation. So first, I guess I want to draw the line. So the line will go from P1 to P2 at time, let's see, say I was thinking of doing something like this. That will mean at time t equals 0 it'll be at P1, and then it will move to point 2 there. But I think I want to make t it be one whole rotation of the disk it takes to go from one to the other. So how do I do that? 1 minus t over 2 pi. No. T needs to, I should have done it right. 1 over, were my brackets wrong? No. A bit confused. 1 minus t, 2 over 2 pi. Oh, what? It must have been my brackets. Yeah, okay. It was doing t over 2, then it was doing pi over 2 times t. Yeah, so it was going 4 times quicker than I wanted it to go. So yeah, it takes one rotation to go from one point to the other. That's cool. Let's also draw in the line. Let's draw it red. That goes from P1 to this point here. Instead of typing it all out again, let's put it in a block. So this is PT equals that. From P1 to PT, I have drawing a line. Disk is at PT, and pt equals this disk. Oh yeah, I need to put this in here now. So mathematica can be a bit confusing for things like that. Now the problem is that, yeah, I also need to do this. See, it draws the trace now, which is cool, but we also want the trace underneath on the disk. Now that can be done. It will have to be done using, well, it could be done using a bunch of different methods, but I'll do it by doing a show then a parametric plot, just like in the code from the previous one I showed. So I want to have another time parameter, so let's type tau, so that's escape t escape, and from just below 0 up to where t is at the moment. And the plot will be this same expression, but rotated. Rotation matrix. How much does it need to be rotated by? It needs to be rotated by t minus tau. I think. No. Ooh, it's kind of cool though. It's going in the wrong direction, isn't it? Tau minus t. Yeah. See, that's cool. It's not quite right though, because the blue thing is actually moving. Let's see. Oh yeah, it's because it should be tau here. Yeah, cool. That's it. Does one a full rotation and draws out what's going on underneath. Now, that was kind of cool animation already, but I want to add a bunch of different ones. One going here, one going across here, one going across here, one going across here, and then maybe do some going down, so that the red lines just make a grid, but the blue lines make a curvy pattern, right? So instead of having P1s defined up here, P2 there, we'll put them in a table. Like enumerate them. So let's try down here. P1s is a list now. I want to vary the y1 between -1 and 1, and say have 5 of them altogether. So it's like this, but what's x going to be? It should be square root of 1 minus y squared. Yeah, so that they are on the circle. And let's just check that graphics point P1s. Yeah, they're cool. Let's make them on the left hand side. 1, 2, 3, 4, 5, and having 6 of them like that. Okay, cool. P1s are now like this. The points where P1 occurs, the first one is here where we draw the disk and the red line. So we want to say for P1 and P1s now. Since P1 is not, I'm gonna no longer used, I'm gonna clear it. Clear P1 makes that fail. For P1 and P, now P2 here. should I write a little function? So I want to, given P2, given P1, I want to find out what P2 is. No, let's just write it straight in, because it's not too hard. So P1 is y coordinate is the same, but the x coordinate is reflected. It's on the other side of the circle. P1, P2, P1. Let's temporarily get rid of a comment like this so that it doesn't cause an error. Okay, so now we have all those guys going across. So they go across at different speeds because they all have to finish at the same time. And also there's one at the beginning, which is one at the top which doesn't move anywhere. And there's no real point in that. So that's a couple of things to fix. Right, let's introduce a variable n, which is how many disks we want. So that turns into n, 2 over n, and that means that we can do, well, maybe this is the best way to do it. 2 up to minus 2. Yes, that excludes those last guys. Now the other thing is, I want them all to go at the same speed. So that means we have to change this formula here for what PT is. And so the distance they have to go is 2 times the x coordinate of P1. So if we multiply the parameter t by 1 over that, it would normalize it, right? So it would actually normalize it just to divide it by the first. Okay, let's just see if this works. So it's a bit crazy. So we're wanting to divide now. Okay, they're going at the same speed, but in the wrong direction. That's because, yeah, P1 is, the first coordinate P1 is always negative. So PT equals negative this and negative this. Whoa! Okay. Wait, hang on. It's P1. Okay, I'm just gonna do it like this. Yeah, okay, so now they all got the same speed. And then push off the edge, which I fix at the end. Fix at the end? Yeah, I guess. Or see, I'm thinking that. Okay. I could say that the maximum this goes to. Okay, I think I'll tidy it up at the end, but at the moment that's drawing that quite nicely. And just to put in the traces underneath in the similar kind of way. Here we go. So again, we want a table over the P1s, so P1 and P1s. And then we copy our expression for PT. It's not so good to copy and paste stuff when you're coding. So it might be better to write it into a function. Now remember, determiners t is fine, but this has to be tau here. Rotation matrix dot. Now why? Okay, missing a bracket. Okay, let's see what happens. Cool. Okay. Well, that one makes this bit here is cool. Is that correct? Let's see. Yeah, it looks correct, I think. I trust it, right? Pretty good. Okay. And now, what about ones coming down as well? Some disks coming down. I can delete this. Right. So this will be of quite similar. Okay, I'll call them P1's 2. I want to vary the x in the same way. I'll have the x changing and the y, so those are at the bottom. Okay. Now I have got all this stuff, comma the new ones. P1's coming from the second list. P1. Okay, and then so there's P2 business in here. I want to keep the x the same, but flip the y. The distance it goes is again, is minus the y coordinate of P1. Let's see what happens. Oh yeah, it should be x. So there's some new ones at the bottom, and they go up. I said I wanted ones going down, but then these guys are going up. They're drawing out a grid, like I was saying, but the blue lines will draw out something much more interesting. So I need to get those other blue lines going. Here we go. P1's 2. So there's a lot of repeated code, I guess, but it's working. So this, just doing the same kind of logic as above, over P1, 2 and P1, 2. So now, yeah, it's drawing out. Whoa. Okay. Maybe it's all rotating too quickly. So maybe I'll add a variable omega, which is this rotational speed, so at the moment it's 1. And then that will, yeah, so then it'll be plus omega t for the rotation of the spokes, which make up the disk here. And then the other thing I'll need to change is the rotation. So that will be all times omega in here. I believe everything else stay the same. So I didn't change omega away from 1, so it's the same. That's cool how the ones that go into the center spiral in, which is like the Coriolis effect. If I want to make omega a half, and the whole thing is rotating less quickly, and it makes a bit more of a intelligible pattern, I suppose. And if I make it a quarter, so it still takes 2 pi units of time for, well, I mean the speed of the disks is the same, but the rotation has changed. That's kind of cool, pattern at the end. But anyway, I think I have something here that I will, well, I've got a couple of things to do, like I need to make the disks stop when they get to the other side of the spinning main disk, and I probably muck around with the colors a little bit, and but I make sure that it's all looking good. But I have kind of a GIF here, so that's all. I'll export this, write something about it, and put it up on my blog. But yeah, thank you for watching. Until next time, goodbye.